So welcome to the Picture Language Seminar. Today we have Rupert Frank. He's expert on inequalities, and we look forward very much to hearing him talk about Lieb-Thirring bounds and other inequalities for orthonormal functions. Rupert's been at Princeton, Caltech, and now is at the LMU in Munich. So Rupert, we look forward very much to your talk.
All right. Well, thank you, Arthur, for the invitation. It's great to be here. And yeah, thanks for organizing the seminar. Even though I usually do not participate, I like to watch the videos in YouTube, and it's really a great selection of different topics in mathematics and physics. And yeah, great. And thanks for welcome to all the participants for joining us here. And I should say that I'm not sure completely about the level of detail that you want to hear in this talk. So if there's anything unclear, please don't hesitate to interrupt me, and I'll do my best to explain things a bit better.
So I just could remark that you're talking about Lieb-Thirring bounds, and you have Elliot Lieb in your audience.
That's right. So the title is Lieb-Thirring bounds and other inequalities for orthonormal functions, exactly. And so the plan for this talk is that I'll tell you first a little bit about what Lieb-Thirring inequalities are and what they're good for. And then I tell you a couple of results that we obtained in the last year or last 2 years or so about these inequalities. And then at the end of the talk, I would like to go to some extensions of these inequalities and directions that are open to be explored. So let me jump right in. Here on the top of the slide, we have the Lieb-Thirring inequality. Okay, so the setting is the following. You're given a bunch of functions, say n, and you assume that these functions are orthonormal in L2 of Rd. D is typically 3, but in gen can be anything. And so orthonormality, as we know it, is meant that the integral of these functions against each other vanish when the indices are different and the functions are normalized to B1. Okay, and then in the inequality, you have on the left side the quantity that you think you have control over, and these are the gradient squares of the functions. And then on the right side, you have the quantity that you want to control, and that is the square sum of the psi squareds, okay, raised to a certain power. There is a single power by scaling reasons that works here, so you don't need to pay too much attention to what precisely the power is. But in any way, so you're bounding a power of the square sum by the sum of the gradient squared. And the inequality says that this is possible with a function k, with a constant k that depends on the dimension, but on nothing else. In particular, and that's very important, the constant does not depend on this number n of functions that are involved in this game. Okay, and that, of course, is the consequence of orthonormality. See, if you would use arbitrary functions, arbitrary L2 normalized functions, then you could take all the psi's equal. So on the left side, you have a sum, so the left side would be n, whereas the right side is, well, this is a sum to a power greater than 1, so this would be n to the 1 plus 2 over d, and such an inequality cannot hold uniformly in n. Put differently, without orthonormality, you would have to choose a constant that does depend on n, and that goes to 0 as n goes to infinity. Now, what's the physical meaning of this inequality? Why did Lieb and Thirring back in 1975 come up with this inequality? And why has it proved to be so useful since then? So what you want to think of is the Slater determinant formed by these functions psi n. So that defines an antisymmetric wave function on Rdn, and that describes n spinless d-dimensional particles. Okay, they are fermionic. That's encoded in the antisymmetry, which you get from forming the determinant. And then, so you have this n-body state, and then what is the left side of the inequality? That's precisely the kinetic energy of this state. And on the right side, the quantity that you have there, the square sum, that's exactly the one particle density. Okay, the probability of finding an electron, or probability times n of finding a particle at x. Okay, now what I said is that this gives you an inequality for Slater determinants. So these are particular fermionic n-body states, but in fact, a simple convexity argument shows that the inequality remains valid for general antisymmetric functions. Okay, but this will not be so important for my talk. So we look at mostly at these Slater determinants. All right, so what does the inequality say? Which physical principles are quantified by it? The first principle is the uncertainty principle. So, right, the uncertainty principle says that a wave function cannot be localized too much, both in momentum space and in position space. The fact that the wave function is not concentrated too much in is not spread out too much in momentum space, that's quantified by the fact that you have a control on the left side, or the assumption that you have a control on the left side. And now when you want to say that therefore the function cannot concentrate too much in position space, well, somehow the worst that could happen is that you get a delta function, right? That you concentrate the probability at a single point. But what you have here is the inequality is that this probability density, or times n, is actually controlled to a power bigger than 1. So therefore it cannot be a delta function. It has to be spread out in position space as well. In that sense, it's a mathematical quantification of this uncertainty principle, and it's closely related to so-called Sobolev inequalities. This has nothing to do with the number of functions. That's a general fact just about these inequalities. When we talk about n, the number of functions, then we see the Pauli exclusion principle here quantified. And remember, this says that the particles cannot occupy the same state, or perhaps put a different way, the particles have to go out of each other's way. Just remember the thing that I said before, when you drop the orthonormality constraint, right, then you could take all the functions equal. That would be a violation of the Pauli exclusion principle. Then the constant would have to go to 0. Okay, that's the case where all the particles are on top of each other. Now, the fact that this constant does not depend on n means conversely that these functions have to stay away from each other. Okay, that you can sum here and sum something to a power greater than 1 and bounded by a single sum. So to show you a picture of this, here are just the pictures of the hydrogen eigenfunctions. So you have the S1, 1s, 2s, 2p, and so on. And you see, so what you see here plotted are the blue and the yellow are the plus and the minus signs. These functions are orthogonal to each other, but you see that in order to achieve this orthogonality, the functions have to spread out more and more. That's sort of what this Lieb-Thirring inequality captures, this fact that in order to have, you have these orthonormal functions, they have to go further and further out so that this sum to the large power is actually, can be controlled by a single sum. Another thing that I want to point out about the inequality is that you're bounding an integral by an integral, okay, which is interesting because that's more or less a classical intuition that if you have something in your system happening at one point, it can, and at another point, then the two things are independent of each other. That's somehow what the inequality seems to suggest. See, if you have the functions psi n supported on one side and another bunch of the psi n supported on another piece, their contributions to the inequality is additive. So that's an important property that's that the inequality has, which is very helpful in the analysis of certain physical systems. And it was this inequality, or all these inequalities that I've listed, that were so that made the inequality such a crucial ingredient in the Lieb-Thirring proof of stability of matter. Okay, and since then the inequality has been used in many different areas, both in mathematical physics, like density functional theory, in PDE, nonlinear evolution equations, Navier-Stokes equation, and this is what I'm gonna tell you later on in this talk, also as a general principle in harmonic analysis. So now we know that we have this inequality. We know, at least I hope, I conveyed an idea of what is useful about it. So what do we still want to know about it? And so the one question that remains open so far is what the optimal value of this constant KD is that appears in the inequality. And in 1976, Lieb and Thirringin made a conjecture, which is still open and which says that there's a dichotomy when it comes to the dimension of this constant. So in dimensions 1 and 2, the conjecture is that this constant is given by the very same constant that you have when you take n equal to 1, when you have only a single function. So that would mean that these particles repel each other, right? So even if you allow the system to have these n orbitals, they want to go very, very far away so that you don't see any interaction between them, and then you get the constant corresponding to n equal to 1. Okay, that's a constant that you can compute. I mean, in one dimension, you can write it out. It's something like, I think, pi squared over 3 or something. In 2 dimension, you can compute the constant up to arbitrary precision by solving an ODE. The situation is conjectured to be completely different in dimensions 3 and higher. Namely, in that case, what you assume is that the optimal constant is attained only in the limit where you have infinitely many such functions, and these functions together form a free Fermi gas. Okay, so it's a homogeneous, they have a homogeneous density everywhere in space. And that's, of course, somehow there, in some sense, the particles stick together. It's the opposite situation from what is expected to happen in dimension n equal to 1. And so then the constant that you would get in this this inequality would be the constant that appears in the Thomas Fermi approximation. Okay, that's an old theory that goes back to the 1920s, which is a statistical theory of an atom. And while it was somehow I mean, it's an approximation in the sense of physics, there have been works, in particular by Lieb and Simon, who showed that in certain limiting regimes, this theory turns out to be exact. And the inequality would say, if it was true that in dimension 3 and higher, this Thomas Fermi approximation is really a rigorous lower bound to quantum mechanics. That would be, I think, a fundamental result in the area, in particular in density functional theory. And I should say that today, Elliott Lieb was awarded the medal from the Erwin Schrödinger Institute. And in particular, in the citation, they mention the discussion and the analysis of density functional theories and these gases. So this is really an important issue. And I would like to use this opportunity to congratulate Elliott to this award. Congratulations. also from a mathematical point of view, I think it's very interesting, this conjecture, because it shows this difference between dimensions. I mean, we're used in many physical problems. There is such a difference that we expect different behaviors in dimensions 1 and 2 and in 3 and higher. But I think it's fair to say that here in this Lieb-Thirring problem, nobody really has an idea or even a heuristic understanding why we should have this sort of repulsion in 1 and 2 dimensions and this attraction in 3 and higher dimensions. So I think this is a very intriguing open problem. Now that I have you brought up to the same page on Lieb-Thirring inequalities and what is known, I would like to present 2 recent results that we obtained concerning these constants or the optimal values of these constants. I should say right away, I mean, we cannot solve this Lieb-Thirring conjecture. It still remains open, still remains a challenge, but at least there has been some progress in the last years concerning what we know. So first of all, I've put up here in the first line of the slide the precise definition of this Thomas Fermi constant. It doesn't matter particularly. And I remind you that the conjectured optimal value of the Lieb-Thirring constant in dimensions 3 and higher is supposed to be exactly this Thomas Fermi constant. And so the best we know about this, the best lower bound we have on this Lieb-Thirring constant so far is that it's a certain constant to the power 1 over d times this semi-classical constant. So put differently, in 3 dimensions, the constant is not smaller than 0.7785 of the conjectured value. So we're off by at most 22 or 23%. And so since, when was that, 45 years ago, when Lieb and Thirring originally made that conjecture, they started out with a value of 0.1850. This has been improved constantly, in particular by Lieb itself. There was about 10 years ago, Dolbeau-Laptev laws arrived at 0.7400, and these are values in 3 dimensions. And as I said, we could improve that again a little bit. And so the hope is that eventually we get rather close. I should say that the value is in 1 dimension is also quite good and perhaps better than it appears here. But anyway, that's a side remark. The other thing is, I mean, this is just a bound. How good can we be? The other thing is, what can we say about these constant and about their, even if they're unknown to us, can we say something about their structure? And what I mean by this is, see, let's look at the inequality. The inequality has naturally a parameter n. The Lieb-Thirring inequality, or the Lieb-Thirring theorem, says that the constant can be chosen independently of n. Fine, but you can still nevertheless insist on defining, on allowing only n functions. And then you get potentially a larger constant, right? And so it's just that, so you have now a constant for each n. And the Lieb-Thirring theorem says that all these constants are uniformly bounded from below by their constant. And I mean, why is it natural to do that? Well, that's exactly what appears in the Lieb-Thirring conjecture. They have the constant where they only allow for 1 function. That's conjectured to be the optimal constant in 1 dimension. So here's a theorem which was obtained last year. It is hopefully going to be published this year. And there we study now how these constants in the inequalities depend on n, on the number of functions. So we know by abstract, I mean, but just by the definition, right, that these constants don't go up. And we also know that so it's a decreasing family and that they're bounded from below and actually converge to that constant which is the optimal constant in the Lieb-Thirring inequality. And so what we proved back then is, very importantly, this is a theorem that only works in dimensions 3 and higher. Then we have a sequence of particle numbers nj, which become arbitrarily large, such that along this sequence, the constants go strictly down. Okay, that's in the spirit of the Libeterian conjecture. The Libeterian conjecture says that in 3 and higher dimensions, the inequality should be attained for infinitely many particles, right, in this free Fermi gas limit. It's not the 1 particle constant, but it's also what this theorem says, it's not the 2 particle constant, it's not the 3 particle constant, not the 4 particle constant, it's not a finite, the optimal constant of the Libeterian inequality is not attained for a finite number of functions. Okay, and so in particular, what we see in this theorem, at least, I mean, the statement is only written here for dimensions 3 and higher. The proof does not work in smaller dimension. And that is actually because the proof is based on a certain attraction of the particles. Okay, so they want to stick together, which is what we want to prove in dimensions 3 and higher, and which is conjectured to be wrong in 1 and 2 dimensions. Okay, so we do see here for the first time a dimensional dependence in these inequalities, but we still don't know what the optimal constant is. And so concerning the real conjecture, we're still away from that. Let me talk about something different, namely another form. It's also called Lieb-Thirring inequalities. These are inequalities about eigenvalues of Schrodinger operators. And this is a family of inequalities. See, before the Lieb-Thirring inequality that we discussed so far, over here, that there was in every dimension, there was 1 inequality. Now, in this Lieb-Thirring inequalities for eigenvalues, in each dimension, you have a whole family of inequalities. They're parameterized by this power gamma. And if that parameter gamma happens to be equal to 1, you get a dual version of the inequality we've been talking about so far. It's not completely obvious, but I hope you believe that, and perhaps you even see sort of a duality appearing here in the exponents, but it's not so important anyway. So what is this inequality, this other family of Lieb-Thirring inequalities about? So you're looking at a Schrodinger operator, 1 particle Schrodinger operator in your Hilbert space, L2 of Rd, and the potential goes to 0 at infinity. And then you have the negative spectrum is discrete and consists of eigenvalues Ej, which are either finite in number or accumulate at the origin. And what this Lieb-Thirring inequality says is how, I mean, it bounds on the size of the eigenvalues. So you take the eigenvalues, take the absolute value, raise it to the power gamma, and sum. And this whole sum is bounded by a constant times an integral of the potential. There's a constant appearing here. The constant doesn't depend on anything except on this parameter gamma that you choose here on the left side and the dimension you're in. Once again, the question that we can ask ourselves is, what is the optimal value of this constant? And once again, Lieb and Thirring in their 1976 paper made a conjecture about it. And the conjecture is analogous to what we talked about before. In fact, for gamma equal to 1, the conjectures are equivalent. And the conjecture says that the optimal constant is the maximum between the 1 particle constant and the semi-classical or classical constant. So what is this? The 1 particle constant, I guess you have already an idea of how one could define that. Well, simply instead of summing here over all the eigenvalues, you only sum over the eigenvalues up to this given number n, right? So the 1 particle constant is just, you say, what is the eigenvalue to the gamma? How can this be bounded in terms of the appropriate integral of the potential? And similarly, you define the n particle or n eigenvalue constant.
Rupert, is V minus the negative part of V?
That's correct. Yes, I didn't say that. Thank you.
And,
so it's only the attractive part of the potential that contributes to the eigenvalues. I mean, that's wrong. I mean, obviously the other part contributes too, but it's if you would put here an absolute value, then you would do better by just throwing away the positive part of the potential. Okay, so we have potentials that are only negative. And so I told you this is the one particle constant, right? Now let me tell you quickly what the classical constant is. And that's sort of the translation of the Thomas Fermi approximation into the picture of Schrodinger operators. And namely, these are so-called Weil asymptotics. And so what you do there is you look at the Schrodinger operator with a large coupling constant in front of the potential. And we're eventually letting this coupling constant go to infinity. And we're going to denote the eigenvalues by Ej of lambda, displaying this dependence on lambda. And then we look at the left side in the Lieb-Thirring inequality. And now this can be written in a more fancy way of taking your operator, taking its negative part, in the sense of functional calculus, raising that to the power gamma and computing its trace. That's a triviality. That's only rewriting it in a complicated way. But the reason why I'm doing this is that Weil calculus or pseudo-differential calculus says exactly that in order to evaluate such traces, what you can do is you can look at the symbol of the operator, which is a function on classical phase space, which is psi squared plus lambda v of x. Now you take the function of that symbol. So again, you take the negative part, raise it to the power gamma, and instead of taking a trace, what you do is you integrate over phase space. Okay, and now this is a simple computation here for fixed x, you can do the psi integral. And then you see simply by scaling, what comes out is, well, lambda v to the power gamma plus d over 2, which is exactly the same quantity as the one we have up here. So in other words, asymptotically, in this large coupling constant regime, or equivalently, you could write a small coupling constant in front of the Laplacian, and would be the limit h bar going to 0. In this limit, we get sort of asymptotically an equality with a certain constant. And then it's obvious that the constant that you get in this way has to be smaller or equal than the optimal constant that appears in the inequality. All right, so now I've explained you what the Libeterian conjecture for the eigenvalues of the Schrodinger operators is. And I should say that this conjecture has been proved in quite a number of cases. In particular, it has been proved in any dimension for values of gamma greater or equal than 3/2. That goes back to the original Lieb-Thirring paper. There is work of Eisenman-Lieb, and then of Laptev and Weidel. Another result where the conjecture is known is in one dimension at an endpoint case. On the other hand, it's also known that sometimes the conjecture is not true. This was shown already, I think, in 1978 by Glaser, Grosse, and Martin. And then another counterexample in a different regime was given by Alfer and Robert. Still, in many cases, the inequality is open, and that includes in particular the case gamma equal to 1, which, as I said before, is the one that relates to the previously discussed family of Lieb-Thirring inequalities involving the kinetic energy. Okay. Now that's a different version of this theorem I showed you before, now translated to the Schrodinger operator language and then also extended. So this is a theorem that's still in preparation. And so we're looking now at these constants. Again, we define the n particle constant, as I said before, by restricting to n eigenvalues. And then again, we're saying that there's a sequence of nj's diverging to infinity such that these constants are strictly increasing along that sequence. That is true under a certain condition. That's this condition. Gamma's got to be greater than 0, and gamma, that's important, got to be greater than this magic value 2 minus d over 2. Or put differently, in the inequality, the exponent of v should be strictly greater than 2. That's the main assumption, and that's the assumption which for gamma equal to 1 translates into this dimensional dependence between dimension 1 and 2 and dimension 3. Okay, in particular, we see that under this assumption, we always have the strict inequality that the 2-particle constant is greater than the 1-particle constant. Okay, so once again, what this means, this is an attraction. Okay, so the particles want to come together, stay together. L1, if L2 would be equal to L1, this would mean that these two eigenvalues want to go away from each other, right? Then the potential would split into 2 parts, and each part would be just a minimizer for the one eigenvalue inequality, because the potentials don't talk to each other. What the strict inequality says is this is a disadvantage to dissociate, so you rather keep the stuff together. And that's sort of the idea of the proof, where we exhibit an exponentially small attraction between 2 distant pieces of V. And taken together with the results that we've seen on the previous slide, this gives you a rather large regime where the Lieb-Thirring conjecture fails. In particular, we got a failure in both in 2 dimensions above 1 and in 3 dimensions below 1. In a rather large regime. But also, as I can say, you can read the fact that this proof stops at 1, you can in some sense also interpret as a sign that at gamma equal to 1, something special is going on, which eventually could make the conjecture at this case true. This result raises a number of questions that we consider interesting. And those concern now optimizers for finite n, but large n. Okay, so you can think of this thing as like a system in statistical mechanics. So for given n is sort of the system size, you look at an optimal potential V. And at least along a subsequence of n, such optimal potentials exist. And then you ask yourself, as n increases, what does this family of V's do? Right? I mean, does it stick together? Does it do the things go away? Do they form some non-trivial structure? Do we see emergence of periodic pieces? We've investigated this both analytically and numerically, and we have some results in that direction, but I don't want to go into that at this point. This would be a whole different talk. Let me just say, I mean, that one can think of this different behavior sort of like a phase transition with respect to this parameter gamma. All right, so let me switch gears and go to something different. Okay, so far we have talked about these kinetic energy inequalities, and then the eigenvalue inequalities. But if I go back to the kinetic energy inequality, let me remind you what that was here. So we had functions. We were bounding their sum. Control. Sorry. The sum of the gradient, the square sum of the gradients, is greater or equal than a certain power of the square sum, where this thing here has the physical interpretation of the 1-particle density. Okay, and the important ingredient was that we have orthonormality, and that allowed us a better behavior of this constant than the one we would have thought, right? The one we would have thought is the one where this constant goes to 0, like n to the minus d over 2. That's the behavior if you could choose all the functions equal. So let me go back here. So the question is this a general principle? Is it so if you take your favorite inequality and you ask yourself, is there a version of this inequality for orthonormal functions? Is this a general principle that is at work here? And if there is such a principle, can we use it for something? I mean, the Lieb-Thirring inequality has proven so useful in so many different contexts that it could, or you could hope that you find something similar in different setups. So let me be a little bit more precise. Let me pick a Hilbert space H, and then I want to have an LQ space where I don't care so much over which measure this LQ space is defined. And I want to look at an operator that maps this Hilbert space into this LQ space for some fixed Q greater than 1. And if this operator is a bounded linear operator, then that comes along with such an inequality. Okay? And now the question is it true that we have a version of this inequality for orthonormal functions? What does that mean precisely? So you have these functions, again, psi n and psi m, have an inner product which is equal to delta and m. Now you apply your operator to each of the functions, take the square sum, right? That has the meaning of a density. Sum this up, right? And then you raise it to the power. The power here has to be q over 2, so that if you have a single function, it reduces to the power LQ that you have originally. Now, it's a simple exercise, is that you have such an inequality where n is the number of functions with the power sigma equal to q over 2. That's sort of the power you get when all the psi's are the same, right? That's the power you get without orthogonality. The question that we ask ourselves, is it true that you have such an inequality with a better power that scales better in the number of functions as the number of functions goes to infinity? And I should tell you right away, at the moment, we do not know a general principle of whether this is true or whether it is not true. That depends really on the operator in question. We do have a list of examples where this works, but the computation of the optimal power sigma that you get there really depends very much on the concrete operator under investigation. And so this question was already investigated, or the first result goes back to Elliott Lieb in 1983, where he generalized a theorem in harmonic analysis, which is called the fractional integration theorem, or the Hardy-Littlewood-Sobolev inequality, where he generalized this inequality to the case of n orthonormal functions. So what exactly did Lieb prove? So you take your functions, your orthonormal functions, you convolve them with a singular kernel, x to the minus d plus alpha, where alpha is allowed to vary in a certain range. Take the absolute value, take the square, you sum, and then you raise it to a power, d over d minus 2 alpha. And so you know if you had a single function, then you would have, then this thing is bounded. Okay, under the assumption, of course, that psi is L2 normalized. But now Lieb's theorem is that this grows at most like n. And now if you look here, what you have, so the effective power, you have the sum to the power d over d minus 2 alpha. And you see, of course, the d over d minus 2 alpha is a number greater than 1. So you bound a sum to a power greater than 1 by n, which is again a manifestation of this orthogonality principle, the principle that these functions have to go out of each other's way. concerning this, the question of applications, already this theorem here of Lieb has a number of important applications. In particular, this is equivalent to the so-called Zwicky-Lieb-Rosenblum inequality, where you bound the number of negative eigenvalues of these Schrodinger operators, again, through an integral of the potential. And so in the last 10 years or so, we've looked at other manifestations of these principles in the area of harmonic analysis. And so the first thing which I present here is a version of the Strichertz inequality for orthonormal functions. And the second thing is a version of the so-called Stein-Thomas restriction theorem, again for orthonormal functions. And let me say right away that both of these theorems do have applications both in PDE and in spectral theory. Let's talk about, for the moment, let's talk about the Strichertz inequality, and let's try to understand what that means. So when talking about dynamics, well, the advantage of, why what we have when we formulate quantum mechanics using Hilbert spaces and self-adjoint operators is that we have a unitary time evolution. Okay, so in this concrete context here, this would mean if we have just the Schrodinger or just the Laplacian actually propagating, this means that the L2 norm of these functions are preserved. Nevertheless, we all know that the phenomenon that we have is that of dispersion. Okay, so it's not only that, of course, so we start with a probability distribution and we keep always a probability distribution, but what we also observe is that this probability distribution spreads out as time evolves. Okay, and that cannot directly, or at least I don't know how to quantify this directly in terms of the underlying Hilbert space. And one way to quantify this is to look at such a nonlinear inequality where you have powers q and here p over q, which are different from 2 or 1 appearing. Okay, so in particular, what that inequality says is that you have a certain integral, and that integrated over time is finite. So in particular, if an integral over time, an infinitely extended integral over time is finite, that means that the quantity that you're integrating in some sense has to go to 0. And that's sort of that you see somehow that this is really a mathematical quantification of this dispersive phenomenon. So let's look at it in more detail. So you start with these orthonormal functions psi n. You time evolve them under the just unperturbed Schrodinger operator. You look at the square sum, the density. Now you raise it to a certain power, integrate over space, raise it to another power, and integrate over time. And the statement is that such an expression is bounded by n to a certain power. And of course, the theorem is useful if this power is smaller than the power that you would expect, right? The power you would expect, you would get, simply from looking at the sum and just, saying that you have n terms here. So the power would be n to the p. And there are certain restrictions on these exponents. I don't want to go into them too much. One restriction just comes from scaling. That's a trivial thing. But then there's another restriction coming, telling you which Qs you're allowed to take. And that's a whole science by itself. What I want to stress here is that this constant that we get, or sorry, not the constant. What I mean is the power, the exponent that we get here is the best possible power. Okay, so what we have in mind sort of is a system in a thermodynamic limit where you really want to get the optimal dependence on the number of particles in order to say something. Quick remark, a side remark, is that there are some cases here concerning values of Q which are greater than that are still not completely understood. And yet another thing is that I was, in the first part of this talk, I was telling you about optimal constants, right? And I was telling you about a one particle constant where you just have one term in the sum. I was telling you about Thomas Femi approximation, where you have this sort of this uniform gas, Fermi gas, and that this were conjectured to be the extreme cases. You could make the same, I mean, think about the same thing here, right? There's an obvious one particle constant. If you think a little bit about it, we'll go through that on the next slide. There's also a generalization of a semi-classical constant for this inequality. As far as I know, nobody has investigated best constants for this inequality. I think that would be an interesting question. But so far, I mean, we're happy that we got these powers right. The other inequality that I want to mention briefly is called the Stein-Thomas inequality. This is an inequality where you have functions on the sphere, okay, and you Fourier transform those. So I mean, this is not an ordinary Fourier transform. You think of these rather perhaps as measures or something, right? They only live on the sphere, but you can still form that integral. And then the function that you get, which is defined now in RD, has certain integrability properties. It's a power d plus 1 over d minus 1 that appears here in this original theorem of Stein-Thomas. And our theorem says, again, that you have a gain in the power. So naively, we would expect here a sum to the power d plus 1 divided by d minus 1 to be bounded by n to the d plus 1 divided by d minus 1. But you have a gain. You only need the exponent d over d minus 1. There's a mathematical similarity between these two theorems. Namely, you can rephrase the Strichertz inequality as a restriction theorem to the parabola. You think of functions as defined on the parabola. That's a parabola in space-time given by the dispersion relation of the Laplacian. And in that sense, they're actually pretty similar. And once you have this point of view, there are also many different generalizations of these inequalities, some of which we've explored together with Julien Sabin in the years following that work. These inequalities, I told you before that the Lieb-Thirring inequalities have applications to eigenvalue bounds for Schrodinger operators. I didn't say it explicitly, but I meant, of course, self-adjoint Schrodinger operators with real value potentials. In some applications, it's natural to look at Schrodinger operators with complex value potentials. And so then you need different techniques to bound eigenvalues. And these inequalities that we got out of these Stein-Thomas inequalities for orthonormal functions and its generalizations, they lead to the best currently known results about Schrodinger operators with complex potentials on the accumulation of eigenvalues at the positive real line. So instead of going through the details of this proof, which, as I say, are, I mean, you make very heavy use of techniques in harmonic analysis. They are somewhat technical. Let me briefly explain how you could guess such a power. And so this should hopefully explain you the physical intuition behind the inequality and also explain or give a motivation for which problems this inequality might turn out to be useful or has turned out to be useful. And to simplify things, I want to look at the particular case where P is equal to 2. Excuse me, where P is equal to Q. That's the particular case where this power is equal to 1. And so then we have to bound only the integral dx dt. And then we can work out what the power is, and it's n to the d plus 1 over d. And again, you see the sum is taken to the power d plus 2 over d. So you have this gain by 1 over d. So here's the heuristics, how we can create a state that achieves asymptotic inequality in that inequality. So what we want to do is at time 0, we consider n electrons in a box of size L with a constant density. Okay. Now, what we're saying is first, the inequality is only really interested up to a certain time t that we don't know yet, that we will compute in a second. And that's roughly the time by which all the electrons have kind of gone far away from this box. They don't see each other anymore, and they just lead their individual life. Okay, now, once this happened, once they're all away from each other, this sum really is just, it's consists of disjoint pieces, so it will roughly have size n, and that's smaller than what we want. Good. So the question is really, what is this relevant time up to which we should look at the inequality? And we think of this time t as a typical time it takes an electron to move a distance comparable with the size of the system. Right? So the size of the box, that was what we called L. Now, Thomas Femi theory, remember, that's what we had at the very beginning when we started talking about Lieb-Thirring inequalities. That has rho to the 1 plus 2 over d. That was the Thomas Femi approximation to the kinetic energy, rho to the 1 plus 2 over d. So that's the kinetic energy. So therefore, the expected momentum per particle is rho to the 1 over d. Right? Because the momentum squared integrated against all the particles, that gives you exactly rho to the 1 plus 2 over d. All right. So therefore, if you now comes an ad hoc assumption, and we imagine that these electrons move ballistically, then what we have here is that this time is roughly the distance times this expected momentum. So, and if I plug in this value of t into that inequality, well, then you see the time integral gives you t. The size of integration, that's roughly still the box. And the density is also roughly still the density you started with. If you plug in these values that we've computed so far, then you get exactly this power n to the d plus 1 over d. Okay, so that's the heuristic. You can use coherent states to make all this rigorous, right? Sort of the length scales are all here, and using this, you can actually justify that this is the correct power. You can also do it for general P or Q. So the inequality is sort of expected to be sharp or optimal when you have such quantum mechanical systems. So that brings me to the end of the talk. Let me summarize briefly what we've done. I've shown you the Lieb-Thirring inequalities. I've explained you in which sense they can be understood as mathematical quantifications of the uncertainty and exclusion principles. And I've shown you, explained, or mentioned that these inequalities have many applications in mathematical physics, analysis, and PDE. We've talked about the quest for the optimal constants in these inequalities, and in particular also for the structure of optimal configuration as you increase the number of allowed functions. And then at the end of the talk, I briefly mentioned that this idea of Lieb-Thirring, that orthogonality needs space, right? That think again about this hydrogen atom picture where these things grow and grow, that this basic idea actually is not at all restricted to this original setup from Lieb-Thirring inequalities, but also that inequalities that are nowadays heavily discussed in harmonic analysis and heavily used in PDE theory, they have versions where this Lieb-Thirring principle applies. And we have proved in some of these inequalities an optimal dependence on the number of functions, and several questions there remain. That's all I wanted to tell you. Thank you very much for your attention. Thank you.
So thank you, Rupert, very much for a beautiful summary of all these nice inequalities.
Thank you.
So let's open the discussion. Perhaps for the moment we can stop sharing your screen, and I would very much like anybody who asks a question to turn on their video so we can see you talking. Maybe I could start by asking, are there any strict arts inequalities that you can replace the root propagation by propagation with a potential?
That's a good question. Thank you. It has been investigated in the one particle setting. So when you have, when you just want to look at the propagation of a single function, then these inequalities have been proved. One needs to be a little bit careful because, of course, if you have bound states in the system, you need to project them out because, of course, they don't disperse at all. What makes things also a little bit hard is you could have zero energy resonances, and they have also very particular dispersion behavior. But if you forget that, I think one can say that there has been quite some progress on the understanding of one particle inequalities for Schrodinger operators with potentials. In the many particle setting, this has not been discussed at all, as far as we know. So that's an open and I think an interesting question. Thank you.
Thank you. Elliot, did you have a comment?
No, thanks. No, I don't. Rupert did a fantastic job. By the way, can you hear me? Yes. Can you hear me?
Congratulations, Elliot. We can hear you, and congratulations on your award.
Oh, thank you very much, Arthur. Thank you. Now, Rupert did a fantastic job of summarizing so many things in such a short time. And so many of the contributions are his, and that's wonderful.
Thank you.
Jörg, you had a comment.
No, I have a question. I understand that the hunt for best possible constants is of independent interest, and it's a challenge. But does it have physical applications? These improved constants.
Yes.
Okay, well, that's a short answer.
I think really understanding the difference between 1 and 2 and 3 dimensions, I think that's a very important thing. There is really something that we completely don't understand, why these fermions are so different or are expected to be so different in these 2 dimensions. That I think is one of the main motivations. And then the other thing is, I think it would be a very, I think it's more than beautiful if it would be true that Thomas Fermi theory is a rigorous lower bound to quantum mechanics. That somehow it sounds to me like a textbook theorem.
Okay, true. That I understand very well, yeah.
So, yes.
So are there other comments or questions? Such a beautiful talk. There must be a lot of discussion.
Yeah, I just wanted to ask, so in this quest for optimal constants, you mentioned that you have some procedure for finding minimizers. So I wanted to ask, what is that procedure and how do they look like?
So Stan, what is your last name?
Srednyak.
Thanks for the question. So, right. So it is mathematically a non-trivial question to prove the existence of optimal potentials. So, in particular, even if you fix the number of particles, and in in particular, there is one case in one dimension at gamma equal to 3/2, if you remember that, which is sort of a completely integrable case, which is very closely related to the KdV equation and with multi-solitons. And so there you have a huge degeneracy of optimal potentials. But leaving that whole block aside, I mean, these possible degeneracies of optimal potentials, leaving all that aside, one can use compactness techniques to show that if you have a strict inequality, that you do have an optimal potential. Okay, so if say, I mean, which is physically very natural, right? So if the 2-particle constant is strictly greater than the 1-particle constant, then you have actually an optimal potential with two bound states. And then you can iterate this. And so you get a sequence of these using compactness tools, okay? You can prove that you have this sequence of potentials with increasing ends. And the question is now, what you do is you would like to pass now to sort of a weak limit. Would like to say, what do these optimal potentials do as you go to increase the number of particles? And one thing which is very important here is sort of how do you normalize the potentials? Of course, you have, a dilation invariance, right? And so this makes a difference because the potentials could become, they could grow, so to speak, vertically, just become deeper and deeper, like in this example of semi-classical analysis that we said, or they could sort of build such a crystalline structure. They could come next to each other, right? They could grow horizontally. And so in particular in this, I should say that this horizontal growth has not been studied in the original Lieb-Thirring paper, and in fact not before this recent paper that I mentioned. And in particular in this completely integral case, we do have a periodic optimizer. Okay, so and we found numerical evidence in a very, very small region that even in 2 dimensions, you might have this formation of periodic structures. Okay, so that's supposed to happen in a certain range. Okay, where you increase n, then you get the particles arrange themselves next to each other. In a different range, that's the most interesting range. In a different range, you have this where the particles just repel each other and only one particle remains, right? And then yet in another regime, you're just supposed to get this constant, this Thomas Femi approximation, where everything arranges itself nicely and flatly over a big region of space, where you do not have a remaining spatial structure. This is all very much under current investigation. And so there were 2 recent papers that we had where we have some partial results. I don't know whether this answered your question.
So you eventually get periodic potentials, right? That's what you're saying.
I said we have an example in 1 dimension of a periodic potential, which is an optimizer. And we have a numerical computation where a periodic potential does better than any other known potential. This is all very, very delicate numerics. You're talking about exponentially small attraction between these particles. But yes, there is numerical evidence for a periodic potential in 2 dimensions in a certain small number.
So you probably can write down a quite explicit expression for this function in terms of maybe a sum of exponents or something like that.
Not that we know of. I don't think. So I think only in the case where you only have 1 function left over, you have an explicit guess for the optimizer, a semi-explicit guess. Otherwise, I think the shape of the optimizer is rather unknown.
Okay. Thanks.
Yeah.
So that finding the optimizers is a very old classical problem, which was difficult. And Elliot, you were involved in the classical inequalities and showing Gaussians are optimizers.
Yes, so in particular,
Yes.
oh, yeah, Elliot wanted, yeah, go ahead.
No. Sorry.
Yeah, no,
You
Elliot,
go
that's
ahead.
very, very nice paper with Gaussian kernels have Gaussian optimizers, which pretty much summarizes the theorem. And one of the questions that is still out there, perhaps I can mention this, which sounds a little bit like this that it falls into the scope of Elliott's paper, but actually doesn't. And that concerns the optimal constant, the Stricherz inequality, right? Where you have the propagator for the Laplacian that has sort of a Gaussian kernel. And the conjecture is actually that optimizers in that inequality are Gaussians. And that has only been proved so far in dimensions 1 and 2 in a situation where an algebraic miracle occurs. But in higher dimensions, this is still open. And I mean, not to speak of any, this is just the one particle level, not to speak of possible conjectures in the many particle setting.
And it's interesting that in the quantum case, the biprojections play the roles of Gaussians.
Mm-hmm. Yeah. Yes.
So are there any other comments or questions?
Well, may I just say something, Arthur?
Yes, of course.
Going back to what Jörg was asking about what good are sharp constants, well, maybe they're not very useful, but in order to discover sharp constants, they usually mean something. That is, there's some extra understanding that wasn't there before. So for just to take an example, the sharp constants in the Hardy-Littlewood-Sobolev inequality, well, nobody cares very much about it. But in fact, finding the sharp constant came from the realization that the problem had a hidden spherical symmetry to it. And that the problem was, which originally comes on Rn, was best viewed as a problem on Sn. And when you saw it that way, everything was spherically symmetric, and it all then the answer became obvious. So finding a sharp constant usually means some extra insight
Yes.
is gained somehow, because they don't come for free usually.
Also, sharp constants give you uncertainty principles.
I'm sorry?
Sharp constants give you uncertainty principles by differentiating.
Yes, they give you, yeah, but that's correct. But I think Jörg's point was we wouldn't care very much whether it was pi or 2 pi or whatever, but it means some insight is needed.
Yes,
that's the point I wanted to make.
Yeah, you found a symmetry.
Yes, and that's right. And so, for example, in there, to take the Sobolev inequality, there's a sharp constant, which was, by the way, first discovered by a physicist named Rosen, but nobody paid any attention to it. But you then find that at least in some versions, the sharp function, the function that gives you the sharp constant, is 1 over 1 plus x squared to some power. You say, so what's interesting about that? Well, that as soon as you see a function like that, you realize this is spherical projection from the sphere onto the plane. And when you realize that, then you realize that the problem really belongs on the sphere, not on the flat space. So that's not just an ordinary function, it's a special function. It has that meaning. So that's just, I just wanted to make that point.
Thank you. Yes.
And
So I see there are lots of inequality experts who are very, very quiet. Maybe somebody else has a comment? Lenny Gross or Xingtun Yao, Earhart. Paula.
I do have a request if you could elaborate on implications for KDV. You mentioned briefly, but I think that would be an intriguing connection if you could elaborate on that.
Yes, so that goes back already to this original paper of Lieb and Thirringin from 1976, and as far as I understand, also some discussions with Peter Lax. And there are so-called trace formulas for the KdV equation, which are constants of motion. And interestingly, these what arises in these trace formulas are exactly these eigenvalue moments that we care about, the integrals of the potential that we care about, and another term which involves the reflection coefficient. And just because the term involving the reflection coefficient has a sign, it can be dropped. Okay, and that simple argument proves the Lieb-Thirring inequality, the Lieb-Thirring inequality with sharp constant in dimension 1, at this case gamma equal to 3/2. Moreover, it tells you that optimality in the Lieb-Thirring inequality are attained exactly at those reflectionless potentials, right? The term where the reflection term that you dropped is actually equal to 0. And those are exactly those multi-soliton solutions that have been, I think, classified even before the analysis of integrability of KdV equation. And so this seems to be, I mean, this is a huge family of potential optimizers. And there are also other versions. That was what I was alluding to before. There are periodic solutions to the KdV equation. And in particular, so you have yet a different, and this is related to this theory of finite gap or one gap potentials. And so those are these periodic optimizers that I was mentioning before, which very interestingly interpolate precisely between the two. Let me say it differently. So in this case, in one dimension, a gamma equal to 3/2, you have equality in the Lieb-Thirring inequality for potential with one, so that with one bound state, with two bound states, with three, with an arbitrary number of bound states. Okay, and then you also have this periodic family which continuously interpolates between the constant potential, that's the semi-classical constant in the Lieb-Thirring language, and the one potential bound state where you have a periodic function which is strongly peaked at one point, right? So you have a continuous interpolation with this in this family of inequalities. And I would imagine that understanding, a better understanding of this, these KdV solutions could even produce more examples of what goes on in the Lieb-Thirring inequality. So for us, it's rather we use knowledge from KdV in order to say something about Lieb-Thirring. And the way we think about this is that, so we believe in general dimensions, there's a phase transition as you increase the parameter gamma, where you start for small gamma, you start in a regime where stuff doesn't bind, where you've just individual clumps. And then as you increase gamma, more and more combine, and at some point you have this formation of periodic patterns. That's sort of a first phase transition. And then the second phase transition is where these amplitude oscillations of the periodic pattern somehow become smaller and smaller, and where you then end up with a completely uniform density. And it seems like by some miracle of complete integrability in one dimension, this whole phase transition is compressed into one point, and you see all the different phases in a single point.
Mhm.
And what we are trying to do in dimension 2 and 3 is to sort of find these examples of these transitions, but now stretched out over a different regime. And so in that sense, the KDV analysis gives us a lot of things to look for.
Okay, thank you very much.
Well, thank you. Thank you.
Okay,
Sorry,
Al has a comment.
Oh, excuse me.
Well, actually,
Hi.
Peter Lee and I actually had some proof of the Lieb-Thirring inequality around 1982, I think.
Yes.
But I think the proof is very good, except the constant is not as good as what we thought. But I think that proof probably can eventually lead to some much better constant. And I don't know, I have not looked at it anymore in the last 40 years, but I think one should still look at that proof more carefully.
Thank you. Thank you for suggesting this. Yes, I completely agree. It's a very beautiful proof. As actually the paper by Lee and Yao has actually two different inequalities. And one has optimal constants for eigenvalues of the Laplacian domain. And then they gave an alternative proof in addition of the CLR inequality with a constant, which is rather good. I think Elliott-Lieb's constant in 3 dimensions is still the best one. But yes, it's a completely different idea in the Liao paper, and would be nice to revisit that. Thank you for that comment.
Yeah, thank you. Nice talk.
Thank you.
Are there any other comments?
Yeah, I just wanted to clarify. So, concerning your numerics, is it more like kind of lattice approximations to space? And is it possible to somehow try to guess the function forms for the optimizers? In particular, there has been a lot of progress on the theory of almost periodic functions and the analytic forms. I was just wondering if you're trying to guess the function form somehow, how would you approach this?
We have not done that. I have to say. I mean, it would be an interesting approach. It would be great if somebody could explore that. I mean, our numerical computations use some finite element methods, which, I mean, do not specifically look for precise form of the functions. The analytical result that we have so far are sort of perhaps a little more abstract, where you do not use so much the precise. I mean, you need a precise form of some exponential decay, even with some polynomial corrections and so on. But so far we do not have a global approximation for the functions. But perhaps this is something we did not do. The other we should have done. The other thing that you mentioned, I mean, with almost periodic functions, we did not look at that at all. But I mean, since we've looked at periodic optimizers, this might again be a very natural next step to see whether one can find something in that direction. I think despite this inequality being 45 years older, so I think there are really many different directions that can still be explored. And yeah, it would be great if you had some ideas about this.
All right, thanks.
So thank you again, Rupert. It was a really great talk. And we'll see you next week when Shen Gao will speak. Bye-bye. Bye-bye.
Bye-bye. Thank you, Arthur. Thanks for the invitation.